Hi, welcome to Lesson 22H, Sets and Venn Diagrams. The goal of today's lesson is to learn how to draw and use Venn diagrams to aid in the calculation of probabilities. So, I've briefly shown what a Venn diagram looks like in the past, and basically we would use Venn diagrams in order to organize bits of data that would have some sort of features in common. There may be an overlap between things. If I were talking about, say, the factors of 32 and the factors of 24, for example. A Venn diagram, of course, first of all, is represented by a rectangle, which represents all the outcomes, which is the universal set. And then there would be different sets or subsets inside, and so we'd have, for example, our set A and set B. And if I'm looking at the factors of 32, I know we've got, I'll squeeze it in down here, 1 and 32, 2 and 16, 4 and 8, and 2 and 16. Nope, sorry, that's already there. 5, 6, 7, 8. No, that's about it. Okay, so we've got those factors. And then the factors of 24 would be 1 and 24, 2 and 12, 3 and 8, and 4 and 6. So I'd write all the factors of 32 somewhere in the set of A. So I'd have 1 and 32. 1 is also an element of B, so that's why it goes in the middle where it's intersecting. 32 is on its own there, 24 is on its own over here, and then 2 is in both, so 2 can go in the middle here, and then 16 would be here, 12 here. 3 is not in both. 8 is though, so I'd have 3 here, 8 here. 4 is in both, so I'd have 4 here, and I'd also have 6 over here. Okay, so of all the factors of 32, all the factors of 32 are in set A, and all the factors of 24 are in set B, and where there's an overlap between them, they would go in the middle in what's called the intersection. So all of the objects in each set, those are called members or elements. So the elements of this set are 132, 216, and 4 and 8, and the elements of set B are written here. This is the whole sample space that we're looking at, which is the universal set that represents every single outcome possible. And generally, the sets inside are represented by circles, as you can see here. When we're talking about set notation we would use what's called braces, these curly brackets. That's how we would represent elements of a set. So if I were to say the elements of set A, I'd say A equals 1, 2, 4, 8, 16, and 32. So that's how I would write that out using set notation. And if I wanted to then state the number of elements in set A, I could say n of A, or the number of elements in set A, and then I just count those off, and there are 6 of those there. Okay, we can do the same thing for set B, same sort of idea in set notation. If there happens to be some sort of set with nothing in it, suppose, for example, there's some set C with nothing in it, then we would say, of course, that n of C is 0. This is called the null set or the empty set, because there's nothing inside, we can also state it n with this symbol is 0. Okay, so that's the null set or the empty set. Remember when we looked at the spinner? Last time we looked at a spinner that I believe had odd numbers less than, I forget what it was, less than 15 or something like that. Here is an 8 sector spinner of all equivalent size sectors, and the universal set in this case are all those values. So the universal set would be 1, 2, 3, 4, 5, 6, 7, and 8. The number in the universal set, of course, would be 8. And if, for example, I said, let's say event A is a number less than 5. No, let's say 4. Number less than 4, then A is the set, 1, 2, and 3. And then the number of elements in set A is 3. Okay, so we can sort of look at that. And if we wanted to hit the spinner and send it flying, we can say, well, if the number of elements in the universal set is 8 and the number of elements in set A is 3, then the probability of A getting a value less than 4 when spinning would be the number of elements in A divided by the number of elements in U, which would be 3 out of 8. Okay, so we sort of looked at that concept in the past. Okay, so now what if there's other things called the complement set, or event A complement. So suppose we've got, again, the universal set. This has nothing to do with this other stuff. I just wanted to prepare these rectangles so it wouldn't look so messy by drawing it freehand. So suppose this is set A, then all of this outside, all of that outside that is a complement. Okay, so a complement is the outcomes in the sample set or the universal set U that are not in A. They're not in set A. Okay, so that's what A complement would be giving you. We've already mentioned the intersection of sets. Intersection of sets is where two sets have overlapping outcomes, and so we could shade this to demonstrate that the intersection is the part of the set, sorry about that, part of the set that's contained in both A and B. So the intersection is shown by this symbol here, the intersection of two sets, and that's some element x such that x is an element of A and x is an element of B. So there's that and that I mentioned to you in past videos, where mathematically and means it has to be in both A and B at the same time. Okay, so A and B share these elements in here. Okay, A and B are subsets of this universal set, and that just means that a subset is completely contained in the other set. Okay, so A is a subset of U, B is a subset of U, meaning that both A and B are within the sample space of U, the universal set. If we move along to, so this is, of course, the intersection of sets. We can look at the union of sets. And the union of sets is when we have, of course, again, two subsets of U, the universal set. And the union of sets means things that belong to A and B, as well as just A or just B. Okay, so the union, which is the reciprocal, if you will, of that symbol, the intersection symbol, the union of two sets would be some elements such that X is an element of A, or X is an element of B, or X is an element of both A intersect B, or A and B at the same time. Okay, so it's part of A, part of B, or both. Okay, so this means that it could be anywhere in that those overlapping rings there. Okay, there are also things called disjoint sets, and disjoint sets are when the two sets don't overlap at all. There's nothing in common at all. So the number of the intersection of that is going to be 0. We can also say that the intersection of A and B is the null set, or the empty set. It also is said that these two sets are mutually exclusive. Okay, that's just a way to describe these two sets that have nothing in common. Okay, suppose we said that set A is, say some letters A, B, C, D, and set B are numbers 1, 2, 3, 4. Obviously, then the set of A and the set of B are disjoint sets because they have nothing in common. And so that's sort of it for the description of Venn diagrams. We will be looking at a few examples tomorrow, of course, and things will become clear as to how we use them and in what ways we can find probabilities and set up the Venn diagrams in order to determine other piece of information about situations that we'll be looking at. So what I'd like you to do, please, is take a look at examples 15 and 16 on page 592. Then you can see how those examples are used in exercises 1, 3, and 4 on page 592. Then after that, take a look at example 17 in page 593 and see then how that concept can be used in practice exercise 5 on page 593. And then followed by looking at examples 18 and 19 and listening to the self-tutor, of course, on page 594. And then you can draw the connection to see how those examples would be useful in solving exercises 6 through 8 and number 11 on page 595. So that's it for Venn diagrams for now. Thanks for watching, and we'll see you in class.